The title of this talk is Introduction to Pharmacokinetics Part 2. The learning objectives are that we'll be speaking about distribution and clearance related pK. In distribution, we'll be talking about plasma protein binding and the unbound fraction, Fu, the blood plasma partitioning, B to P ratio, the volume of distribution and its different forms, such as volume of distribution initial, volume of distribution of the central compartment, volume of distribution at steady state. We'll move on to talk about clearance and half-life. Plasma protein binding. The free fraction or the fraction unbound Fu is the fraction of the drug present that is not bound to proteins. If plasma protein binding ppb was 90%, then the fraction unbound Fu is 10% as a percentage or 0.1 as a fraction. At equilibrium, the free concentration will be the same throughout the body, assuming no active process. It is the free fraction that is considered to be available for distribution, for interaction with receptors, metabolizing enzymes, and renal filtration, and others. So the free fraction is very important as it is the only fraction that can engage with the target organ and the receptors therein. Note, we usually use plasma for our pK determination. However, blood is the true central compartment. pK parameters when derived from plasma will need sometimes to be corrected for blood when the B to P ratio is more than 1. In these instances, there could be an overestimation of the clearance if the B to P ratio is more than 1 unless we correct for B to P ratio. Volume of distribution. The volume of distribution is the theoretical volume required to accommodate all of the drug in the body at the same concentration as that observed in plasma. Or it could be also defined as the apparent volume into which the drug likes to distribute. In this example, we have the amount of the drug at 1000 microgram going into a beaker of 1000 ml volume. The sample concentration in this instance will be 1 microgram per ml. The amount divided by the concentration will give us the required volume that we need. In this case, 1000 micrograms divided by 1 microgram per ml will give us the volume of distribution of 1000 mils. Distribution can be visualized as shown in this slide, where a drug is absorbed into the body. It goes into blood and it can go from blood to tissue A, tissue B, or tissue C and be distributed forward and backwards between the central compartment and the various tissues. This process is what distribution is. But equally, the drug can be in blood and be eliminated irreversibly. This will be clearance. Distribution. Distribution to any given tissue is governed by how quickly is the drug delivered to the tissue. This is the perfusion rate. And once it's been delivered, how quickly does it get in? This is the diffusion rate. And how much of the drug can the tissue accommodate? This is the extent of diffusion. A basic pharmacokinetic premise is that only the unionized, unbound free drug is available to diffuse between blood and tissues. Therefore, highly ionized drugs can exhibit diffusion rate limited distribution. Distribution can be determined by determining the initial concentration of the drug and the amount given. So if you want to know the volume of distribution is the amount given, in this case nanogram of the compound given, over the concentration achieved in circulation, which is nanograms per mil. If we do this, this will give us a volume, which is the volume of distribution. In this example, we can look at it following an intravenous administration where the intravenous dose divided by the initial concentration achieved gives us the volume. In fact, this equation is made use of when we are thinking of the loading dose to give to a patient for the first time, because we know the volume into which it can distribute, we know the target concentration that we are aiming for, so the multiplication of the target concentration C naught by the volume will give us the dose that we need to start with this dose. I should state that in reality, distribution is not instantaneous, although it's often too rapid to be observed. But if we must determine distribution, we want to extrapolate the plasma profile or the blood profile to the y-axis where we can get the C naught, and this C naught could be used for determining the volume. Distribution and the volume of bodily compartments. This table is being showcased to reveal how much the different bodily compartments are and to look at the extent of distribution to those parts of the body. The volume of the plasma is 3 liters and the volume of blood is 5 liters. The lymph is 10 liters. The intracellular water 27 liters, the extracellular water 15 liters. The total body water, which is the sum total of all of these different body water, comes to 42 liters. This can be normalized per kilogram, assuming that the standard average weight for a man is 70 kilograms. So the total body water is now 0.6 liters per kilogram. This can be very useful in determining the extent of distribution of any compound. So compounds that have distribution in excess of 1 liters per kilogram is distribution beyond total body water, and this is indicative of the fact that this kind of compound likes to distribute widely. The preferred estimate of volume of distribution is volume of distribution at steady state, which is a product of the clearance in blood or clearance in plasma multiplied by the mean residence time. The mean residence time is the average time a drug resides for in the body. MRT can be visualized as the fulcrum of plasma concentration versus time profile. So it's the average time that the drug resides for in the body. What is the volume of distribution? It does relate the amount of drug in the body at any one point to the amount at measured site, whether it's blood or plasma. It is effectively a dilution factor. There are, as said earlier, there are 3 types of volumes of distribution. There is initial volume of distribution, VD, which is the volume of the space that the drug equilibrates with instantaneously. There's a volume of distribution based on the cell compartment or the terminal half-life, VD beta, which is the volume of space associated with the terminal phase. And of course, steady-state volume of distribution, VDSS or VSS, which is the volume of space that the drug occupies at steady state. Generally, the volume of distribution is an hypothetical value. It rarely corresponds to a physical value, but sometimes it can. So an example is the total body water would have a volume of distribution of 42 liters, and if it's normalized per 70 kilogram man is 0.6 liters per kilogram. But the volume of distribution determined can vary from as little as less than 1 liter to more than 50,000 liters for a 70 kilogram man. When we get values which exceeds total body water, it is simply indicative of the fact that this particular drug likes to distribute extensively, particularly in patients which may have excess adipose tissue, as in obese patients. The effect of lysosomal uptake is more profound for diabasic compounds such as azithromycin when compared with erythromycin. The theoretical lysosomal plasma ratio of 160,000 because of lysosomal trapping is registered by azithromycin. Azithromycin achieves a high in vivo tissue to plasma ratio of up to 100-fold and is found predominantly in the lysosomally rich tissues. In this instance, we are looking at what separates erythromycin, volume of distribution at 0.5 liters per kilogram, compared to azithromycin at 62 liters per kilogram. The main difference between them is the fact that erythromycin is monobasic and azithromycin is dibasic. So dibasic compounds tend to ionize and be trapped in the lysosomes, thereby increasing their volume of distribution. Clearance. Clearance is a volume term. The volume of blood or plasma from which drug is irreversibly removed per unit time. Clearance is the irreversible removal of the drug from the site of measurement, usually plasma, per unit time. Clearance processes are additive. We have hepatic, which is both metabolic and biliary. We have renal, which is filtration and secretion. And we have clearance by other organs such as the gut, the lung, by organ uptake, breath, sweat, milk, and even in placenta. A clearance by an organ is limited by the blood flow to that organ. We look now to single dose PK, which in the simplest case, drug remains in the central compartment, primarily blood. It is eliminated according to the elimination rate constant. So drug is given intravenously, it goes into the central compartment, and it is eliminated at a rate of elimination KEL. It is usually and generally a first order process where the rate of elimination at any given time is equal to the elimination rate constant, which is multiplied by the amount remaining at that time. Since the amount remaining declines with time, thus the rate of elimination also declines, and we observe an exponential decline in plasma concentration. Since the elimination is the first order process, a semi-natural logarithmic plot will yield a straight line whose gradient is the negative of the elimination rate constant KEL. So this is the exponential decay curve, which when we take the natural log of it becomes log transformed to a straight line with a negative slope. The half-life can be determined from the KEL, which can be simply the rate over the log of 2 over the rate will give us the half-life. Calculating the half-life. The elimination of any drug follows a first-order exponential decay, which can be mathematically written as shown in equation 1. the concentration of a drug at any time is the initial concentration multiplied by the exponent of the rate of elimination times time. If you take natural log of equation 1 to convert the curve to a straight line equation as shown in equation 2, the equation becomes the natural log of concentration at any time t equals the natural log of the initial concentration multiplied by the rate and the time. We can solve for t as shown in equation 3, where t is the natural log of Ct divided by Co divided by the rate and the elimination. When the concentration is half, the time will also be half as well. So hence the half-life is the natural log of 0.5 divided by the rate, or minus 0.693 over KEL. The relationship between clearance, volume, and half-life. Clearance, volume, and half-life are interrelated. Clearance is, as we said, is the volume of blood or plasma from which drug is irreversibly removed per unit time. So clearance can be written as clearance equals the rate multiplied by the volume. The volume, we said, is apparent volume required to accommodate all of the drug in the body at the same concentration as that observed in blood or plasma. Therefore, the half-life is proportional to the volume and inversely proportional to the clearance. If we substitute the equation into each other, we will get a combined equation that says the half-life is 0.693 Vd SS or Vd beta over clearance. This equation is very unique and pivotal in moderating half-life of a drug. To extend the half-life of a drug, we may increase the volume of distribution, or we can decrease the rate at which the drug is being cleared. On these two premises lies the ability to modulate the half-life of a drug. Determining the exposure or calculating the area under the curve, AUC. The area under the curve of any profile, whether it's intravenous or oral, can be determined by converting each of the sections of the area into trapezoids and finding the area of each trapezoid and adding them together will give the total area under the curve. So the area of a trapezoid is the difference in time between the two parallel lines and the half of the A and B, which are the parallel lines. So when we get this for one trapezium, we can do it for different trapezoids and then add them together to give us the collective of the AUC. So the area of the trapezoid is T2 minus T1 multiplied by half of A and B, which are the parallel sides. Calculating clearance and bioavailability. Clearance is best determined from an intravenous dose administration, and that clearance is dose over AUC IV. So clearance, whether it's in blood or plasma, is dose IV divided by AUC IV. If we were to determine clearance from the oral route, we have to do clearance over F, which accounts for the actual amount of it that is bioavailable. The bioavailable dose or the bioavailability can be determined by the quotient of AUC oral relative to AUC IV multiplied by the dose correction, in this case dose IV over dose PO, when multiplied by 100 will give us a percentage, or it can be expressed as a fraction of 1. Multidose PK. In multidose PK, the rate of elimination of a drug will increase as the amount in the body and the plasma concentration increases. So starting from a low concentration and at some point reaching maximal concentration where the rate of output is the same as the rate of input. At some point, the elimination rate will equal the rate of drug input, and the rate of change of drug amount and concentration will then be 0. When this happens, steady state has been achieved. It generally takes between 3 and 5 half-lives to reach steady state. Multidose PK for the oral route. Multidose PK for the oral route are governed by the same principle as for infusions. Instead of infusion rate, we now have a drug input rate which depends on the dose size, the dose interval, bioavailability, and absorption rate Ka. So we start from a concentration where there is very little drug in the body, rising upon each dose till when a plateau sets in and steady state is achieved. This same graph can be looked at in this way, where each blue line is a repeat dose of each oral dose intake till such a time when steady state sets in. These are the consequences of poor PK. We can have poor absorption, poor solubility, permeability, or extensive force-pass metabolism, and if this happens, there will be no systemic exposure. When we have inappropriate distribution, the drug might not reach the target site. When we have extremely large volume of distribution or tissue uptake, there will be low circulating concentrations of the drug. If we have high protein binding, there will be low active concentration of the drug. And if we have rapid systemic clearance, there will be short duration of action. Application of pharmacokinetics in drug discovery. This table serves to indeed showcase what each PK parameter stands for and how they are applied in making PK decision in the drug discovery setting. The area under the curve AUC exists to measure the level of exposure and to calculate clearance and bioavailability. The initial concentration C0 is to calculate the initial volume of distribution. The volume of distribution, whether initial, central, or steady state, VDI, VD beta, VDSS, they're there to know how widely the compound likes to distribute in the body. Clearance, whether it's plasma, blood, renal, or by any other means, exists to measure how quickly a compound is being irreversibly removed from the systemic circulation. The elimination rate KEL is there to calculate the half-life, and the half-life is to determine the frequency of dosing because it determines the time taken for the concentration of the drug to decrease by half. The mean residence time, MRT, is to know how long the drug remains in the body for. The maximum concentration achieved by drug after administration, except for after intravenous dose, is Cmax. It exists to estimate if pharmacology is driven by Cmax, or by Cmax over MIC, or by time above MIC or AUC. The time to reach maximum drug concentration, Tmax, is to estimate any delay in absorption, such that a good drug will be maximally absorbed by 1 hour, and the further the Tmax comes, the more delayed the absorption is for that drug. In summary, the DMPK properties of drugs depends on many factors, including but are not limited to the physical, chemical, and molecular properties, interaction with lipid membranes, interaction with endogenous proteins, susceptibility to metabolism and other clearance processes such as transporters, the physiological pH, the pathology, and the anatomy. Of course, there's the influence of genetics, environment, food and diet, disease, and polypharmacy. Most of these factors have some interrelation and require an holistic consideration in order to build up an understanding of PK. Thank you for your attention.